Now, a suggestion sometimes recommended is to offset the wind over pressures is to increase the total area of natural ventilation per reservoir. In other words, they're saying, well, I know, let's just put more ventilators on there and it'll stop the problem. Well, no, that's not going to work, because the overpressure is, by very definition, force per unit area. So it doesn't matter if you've got 6 vents or 20 vents. You'll have 20 vents not working, not 6. It's got nothing to do with the quantity. It's actually blowing it back in again. And in fact, it could indeed exacerbate the whole thing by allowing even greater quantities of air to be driven through the vent, so pushing more smoke in. So in this case, you must install mechanical ventilation. So you can't just increase the area to compensate. If it's not working and you can't find a solution, you must install mechanical ventilation. Now that covers the most common problems encountered with ventilators being installed correctly. Now clearly, if a mechanical system is installed to overcome the wind effects of natural ventilators, then they will have to be able to overcome the wind effects themselves. So they've got to have a certain extraction rate to do this. In other words, you should increase their volumetric flow rate to ensure the design criteria is met. So if you're putting them in because of the wind, then you must add a safety factor on to increase the volumetric flow to make sure it can overcome them, because it is going to have an impact even on mechanical ventilation. Now the next phenomenon I'm going to consider is the stack effect. Now the stack effect can have a significant impact on the temperature difference between floor and ceiling height. So what is the stack effect then? This is the upward or downward movement of air or smoke as a result of temperature differences between the inside and the outside of a building. And this shows you here how the stack effect works. Now, when the temperature outside is lower than the inside temperature, for example in winter, what happens is air will enter the building below the neutral plane. You see the neutral plane? And it exits higher up. Now, in this situation, the air and smoke will move upward throughout the building. Therefore, in a very high apartment in the middle of winter, the pressure differentials across boundaries and the upward movement of smoke can actually be very, very significant. For example, a 30-storey building with a typical inside temperature of 21 degrees and an outside temperature of 0, the pressure differential at the top can be as high as 100 pascals. And they think, what does that mean? What's 100 pascals? Well, if you think about it, that's 7 times the pressure created in a post-flashover fire, which generally is about 15 pascals. So it's 7 times more pressure than the pressure created by a post-flashover fire. This here shows you how the reversed stack effect works. When the outside temperature is higher than the inside temperature, for example in the summer or when the air conditioning is in operation, what happens is air will enter the building above the neutral plane, as you can see here, and it exits lower down. Now, in this situation, the air and the smoke will spread throughout the building lower down, so it spreads the smoke down the building. Now, it's important to remember that this stack effect increases with an increase in height and with temperature differences between inside and outside. So this is very relevant to very tall buildings, or on very hot days, or on very cold days. This will have a bigger impact. Now, as you can appreciate, this phenomena is very significant in fire safety, for example, in high-rise residential buildings. So you have to consider the stack effect.